Angular momentum of classical orbit is given by L vector, which is equal to R vector cross P vector. Total energy of the orbital motion, such as planets around Sun, determines the average distance of the planet from the Sun. So for a given total energy, there are many different possible orbits, from nearly circular orbit of the Earth to a highly elongated elliptical orbit of the comets. Here in the diagram I am showing circular orbit for which angular momentum attains a maximum value. For a highly elliptical orbit, L will be 0. In order to give the complete specification of the orbit, it is required that we not only give the magnitude of angular momentum vector but also its direction, just like in case of any vector. To completely describe the angular momentum vector, we require three numbers, which are its components along x-axis, y-axis and z-axis. We also need the magnitude of the angular momentum vector and two angular coordinates that gives its direction, just like latitude and longitude on a sphere. Now this was the angular momentum of a classical orbit. Let's look at the angular momentum in quantum mechanics. Quantum mechanics gives us a very different view of angular momentum. Angular momentum properties of a three-dimensional wave function are described by two quantities. One is L, which is an angular momentum quantum number. Another is M subscript L, which is a magnetic quantum number. Here, angular momentum quantum number determines the length of angular momentum vector. So if you know the value of angular momentum quantum number represented by small l, then you can find the magnitude of angular momentum vector by this formula. Here, L can take values 0, 1, 2, 3 and so on. The magnetic quantum number tells us about one component of the angular momentum vector, and usually we choose z component Lz. Here, Lz equals to ml h cross. ml can take values 0, plus minus 1, plus minus 2, so on up to plus minus L. So if you know the angular momentum quantum number small l, then you can find out the possible values of ml and then find the value of Lz. If you note, for each value of L, there are 2L plus 1 possible values of ml. So unlike the classical angular momentum vector, the quantum angular momentum is described by only two numbers, L and ml. However, clearly, two numbers cannot completely identify a vector in a three-dimensional space. So something is missing. So we will find out this thing later on with the application of uncertainty principle to angular momentum. Now let's find out the components of vector L along z-axis and the angular directions. Cos of theta equals to Lz divided by the magnitude of the angular momentum, and it is also equal to this. Now what is this angle theta? Let's look at that. If this is z-axis and you have a vector of magnitude L given by that formula, then this is the angle theta that it makes with the z-axis. And the projection of that vector along z-axis will give you the component of angular momentum along z direction, that is Lz. Now let's look at a special case or an example for when L is equal to 2. And what we will look at is, we will find out the values of the two quantum numbers, the magnitude, and also the angular momentum component along z-axis. The magnitude of the angular momentum vector is given by this formula. It comes out to be square root 6 h bar. Now, if angular momentum quantum number L is already given in a numerical problem, then all we have to find is first magnetic quantum number ml, which can take values between 0, plus minus 1, plus minus 2, all the way up to plus minus L. Now in this case, because plus minus L is going to be plus minus 2, that means ml can take values 0, plus 1, minus 1, plus 2 and minus 2. So values of Lz, that is there are 5 possible z components of L vector, and those values are 2h bar, 1h bar, 0, minus h bar, or minus 2h bar. Now if you have to represent these vectors, how will you represent it? So let's look at that. You have z-axis and you have a L vector. The magnitude of this vector is always going to be given by this. So I'm not going to write that. Let's not look at that. This vector is corresponding to Lz equals to 0. So we'll find out. So for that, ml is equal to 0. Similarly, you have 4 other possibilities. All these vectors are of length square root 6 h bar, and these are different components along z-axis. Possibilities are plus 2h bar, plus 1h bar, 0, minus h bar, and minus 2h bar. And you can also find out corresponding angle using the formula discussed previously. Similarly, you can solve this for any value of L. So for example, if L is now given as 1, there are 3 possible values of ml. ml can be minus 1, 0, or 1. Corresponding z components can be minus h bar, 0, and h bar. And you can again find out the angle as cos theta equals to minus 1 by square root 2, 0, or plus 1 by square root 2. And that means theta values are 45 degrees, 90 degree, or 135 degree. Now we got square root 2 value because magnitude of L vector is square root 2 h bar. So we saw these 2 examples, and similarly you can do other numerical problems. Just remember, if you look at the above diagram, the angles are measured from here. So this, for example, in this case is here, this angle, or this angle, and so on. So just remember from what point you are measuring the angle. Now let's look at, if instead of L value, like small l equals to 1 or 2, we looked at these 2 cases. If instead we give you the value of principal quantum number n, what happens? How can you calculate then? So for any given n, there can be L value can be 0 and so on, all the way up to n minus 1. So for example, if n is 2, then L can be 0 or 1. If n is 3, then L can be 0, 1, 2, and so on. So if we see the value of L, maximum value of L is going to be n minus 1, and you will use this in one of the homework problem.